Hi, and welcome to College Algebra 2.2, talking about functions. So let's get into it. So a relation is a rule that relates two quantities together, and for the sake of simplicity, we often use x and y. There are two different quantities, usually measuring different things. We often do it as a rule. So a rule in math is an equation. So there are a couple ways you can do input-output tables, ordered pairs, graphs as well, along with those equations. A function is a specific type of relation for which every x value there is only one y value. So they say x's are one to one, aka you cannot repeat x's. You cannot repeat x values. So looking at this table over here, I have no repeat x values, so I'm perfectly fine. This would be an example of f of x equals x plus 2, and we can see that I have no repeat x values. This would be, a line. F of x is just another way of saying y. They're both the same thing. So what would this look like? Well, if I'm looking at input-output table, I see that I have two x's repeated, so this would not be a function. And here, we're using that exact same model right there with that one is being repeated. The easiest way to tell if you're given the graph is what's called the vertical line test. The vertical line test states if I can draw a vertical line, again, assuming it's a perfectly straight vertical line, and I hit the graph more than once, it is not a function. So, well, x equals y squared is a relation. It is not a function. Which should make sense. Quick detour. If we recall, last or in the pre-unit or chapter 1, when we were trying to do x equals y squared, and we talked about symmetry. When we tried to graph that in our calculators, the y equals, we can't mess with anything over here, so we had to get y by itself. So when we square root, we got y equals the square root of x, which looks like this. Well, if I flip back, that is not the same graph I have here, because I'm missing this component right here. But recall, because we square rooted, we have to take in consideration the plus and minus values of square roots. So what turns out is these are two separate functions as one relation, but they're not a function together. So the vertical line test, no matter what, I can draw infinitely many vertical lines. If I never hit the graph more than once, it is a function. But if I hit there more than once, it is not a function. Well, let's talk about some more function notation. So function notation, as we just talked about, was this f of x idea, where f of x is the same thing as y, or it's my output. Well, if I get this idea of f of 2 instead of f of x, what's the only thing that changed? Well, this x became a 2. So all that happens is we're going to plug in 2 for x. So I'm going to plug it in everywhere there's an x, and I just solve. And this would be my output or my y value. And this is my input or my x value. So we get the coordinate of 2, 7. Now, I could even go further and plug in 2x for x. And I would do, obviously, 2x times 2x equals 4x squared. That's why I get 4x squared there. And then quick reminder when we're doing stuff like this, that these are not equivalent. You cannot distribute the square root. That's bad. You would have to FOIL the whole thing out. So you get x squared plus 4x plus 4. You lose out on the middle term there if you don't FOIL it. Or, I'm sorry, the distribution property of multiplication, not the distribution property of exponents.
exponents can only be distributed when you are multiplying or dividing. So that could be distributed across the board, but not for addition or subtraction. Something new is piecewise functions. Piecewise functions are multiple functions together that have certain conditions. For example, in this case, x is less than or equal to 1, we use 2x plus 1, and x is greater than 1, we use x squared minus 1. So let's look at some values here. F of -1. Well, -1 is less than or equal to 1, so I would have to plug in the -1 into my first equation. So I'd get 2 times -1 plus 1. 2 times -1 would be -2, plus 1 gives me -1, which is exactly what my answer says it should be. F of 0, well again, 0 is less than or equal to 1, so I'm going to plug it into the first equation. So I get 2 times 0 plus 1, which would give me 1. Next one, f of 1, well, 1 is less than or equal to 1, so I'm going to plug it into the first equation. 2 times 1 plus 1 would give me 3. F of 2, well, 2 is greater than 1, so I actually have to plug this 2 into the bottom equation. So I get 2 squared minus 1, which would be 3, and so on and so forth. So let's take a look at these individual pieces. Well, here, this first equation in red, if I were to just graph y equals 2x plus 1, that's obviously linear in nature. And if I were to graph y equals x squared minus 1, that is obviously a parabola, and it's going to have a U shape. So let's graph both of those. We kind of get that here. So I get this when x is greater than 1, I get this x squared minus 1 parabola right here. Over here, when x is less than or equal to 1, we get that 2x plus 1 linear shape. My next question to you, does this fail the vertical line test right here and make it not a function? Actually, it doesn't. And this all is a function. The reason's actually pretty interesting. Let's say I'm going back to when we graphed inequalities. So let's say we have that. Well, if I'm looking at the blue, my inequality is x is greater than 1. When I graph that, I'd have an open circle, arrow pointed to the right. And if I were to graph x is less than or equal to 1, I'd have a closed circle, arrow pointing to the left. So here's actually what happens. We get a closed circle right there. We get an answer there. We also get an open circle right there. So when we go to do our vertical line test, we hit the green dot, but we phase right through the open circleness right there in blue. So it doesn't fail, and this is a function. Which should also make sense. The big issue with things not passing the vertical line test is I don't know where to put my x value. So for example, if this inequality was equal to, and this was a closed circle, which would mean this is equal to, when I'm trying to evaluate x equals 1, I don't know which equation I'd have to plug it in for. But because this doesn't exist, I know clearly that I'm going to plug it into the first equation and I get no conflicts. Last thing we're going to talk about is obviously domain and range. It's always nice to talk about. Domain, recall that it are the possible x values, and range are the possible y values. Implied domain are mathematically all possibles.
like when we talk about all real numbers from, negative infinity to positive infinity. Irrelevant domain are appropriate for the actual things. They're a little bit more restrictive. We try to look at those as like the realistic values. An example would be something to the effect of a shepherd counting his sheep, right? There's no restriction on the amount of sheep he could have. He could approach infinity, but mathematically speaking, he wouldn't approach like negative infinity. And he also wouldn't have decimals of sheep or, fractions. So it wouldn't be all real numbers. It'd be something like 0, 1, 2, 3, and etc. So that's an example there where it's just different. Now, domain. We've talked about it before. There are three restrictions. Can't have zeros in the denominator. Can't have negatives under even roots. And you can't take negatives or zero inside a logarithm. The range or the y values, that's usually impacted by those domain restrictions. We don't look for those as much. So let's take a look. This first one. Well, I see that I have an even square root, so I know that x plus 3 has to be greater than or equal to 0, because I can't do the square root of a negative. So I can subtract 3, we get x is greater than or equal to negative 3. So my domain would be negative 3 to infinity. Interestingly enough, that's kind of what I get here, going towards positive x infinity to the right. Now, this provides me with a fixed endpoint with this equation. Interestingly enough, I can plug that in for x. So when I'm looking at my range, we would get y equals negative 3 plus 3 under the square root, which gives us y equals 0, which should make sense. Looking at this, I get that fixed endpoint as well. So my range actually never goes below that. So I get a range of 0 to infinity because it's going up towards positive y infinity. Number 2 has no square roots, has no fractions, and has no logarithms. So I see 0 domain restrictions. So my domain would be all real numbers. So negative infinity to positive infinity, or the double R for all real numbers. Range, I have to look at the equation because there's a couple things that could go wrong. I see that I go down to negative y infinity forever. I go up to positive y infinity forever. So I get, the same thing, all real numbers. Number 3, I see that I have a fraction. So I know that x minus 2 cannot equal 0. So I can add 2. We get x equals positive 2 as something it can't be. And we see that actually graphically right here at this x equals 2. That is called a vertical asymptote. So when I go to write my domain, I get all the negative x infinity values and all the positive x infinity value except for 2. So my domain could be negative infinity to 2, union 2 to infinity. Interestingly enough, when I talk about my range, I go up forever and down forever, so I actually have no restrictions there. Except for potentially this y asymptote here at y equals 1. For the sake of today, we'll just keep it simple. Over here, we get, if you want to really do it, negative infinity to 1, union 1 to infinity. And this should make sense because this fraction is never going to equal 0. Here, I get a parabola, so I see no domain restrictions because I'm not dividing by, I don't have a fraction, I don't have a square root, I don't have a logarithm, so I get all real numbers. But when I go to look at this parabola, I do have this minimum right here at, let's say, negative 1.5 and negative 4.
I never ever go below that value in terms of the range, but I do hit that value. So I'd say my range is -4 to infinity. Thank you for listening, and I hope you have a great day.